pleasure to introduce Professor Aditi Sende. She is Professor of Physics in Harish Chandra Research Institute, Prayagraj, India. And so I'll say a few words about her work before she takes over. Along with Professor Ujjwal Sen and Arun Kepati, she started the Quantum Information and Computation Group in HRI in 2009. Currently, the group consists of 3 faculty members, Arun Kepati, Ujjwal Sen, Aditi Sende, around 22 PhD students and 5 postdoctoral fellows. Professor Day did her doctoral work in the University of Gdansk under Professor Marek Zukowski and subsequently was an Alexander von Humboldt postdoctoral fellow with Professor Maciej Levenstein in Hanover. She was also a Raman E. Kajal fellow in ICFO, the Institute of Photonic Sciences, Barcelona, and an assistant professor in the Jawaharlal Nehru University, Delhi. She has received the Booty Foundation Award for Excellence in Theoretical Physics, Astrophysics, and Biophysics in 2012, and the Shanti Swarup Bhatnagar Prize for Science and Technology in 2018. She is a fellow of the Indian Academy of Sciences and the Indian National Science Academy. So I welcome Professor Aditi Sende and tell us about quantum information and computation. Over to you, Aditi.
Thank you very much for your kind introduction. And thank you very much for the invitation. So now I share my screen. Can you see my screen? Is it visible? Hello? Okay, yeah. Okay, it is visible. Okay, so I will talk about technologies in a quantum world. So in other words, I will talk about quantum technologies. So in next 15-20 minutes, I will try to give you the flavor that why we really want to work on quantum technologies or we want to build quantum technologies. So the technologies that we use nowadays are, say, for example, desktop, laptop, where I'm giving this talk. So these are quite useful, but the aim is to build quantum version of it. Now, similarly, we also use, for example, communication technologies like internet, which I'm using to give this talk. And say we use data, we use mobile phone, etc. So these are communication technologies. At the same time, we also use other machineries like batteries, refrigerators. Our aim is to build quantum version of them. So for example, we want to build quantum version of the computer, quantum version of the communication technologies, which are known as quantum communication, and the quantum batteries and refrigerators, sensors, etc. Now, the question that probably I will try to answer in next 15 minutes, that why we want to build these technologies. So let's start that why we want to build quantum computers. So the computer that we use, say, for example, this desktop, laptop, even say, for example, these workstations, which are very powerful, they are useful in different sectors. So, for example, in government offices, in railways, in industries, education sectors, banking, etc. So at the same time, they are also useful to perform certain mathematical calculations, to solve certain mathematical problems. Now, in classical computer, the basic unit is bit, which is one of the zeros and one. And in a classical computer, we can think that there are 3 steps that usually we follow. First, we give input to the computer, which can be translated in strings of zeros and one. Then there are some logical gates has to be performed. So these actually manipulate these bits. And finally, we get some output, again, a strings of zeros and ones. Now, let us first consider a problem that we want to solve, say, for example, in a classical computer. So I will give you a number and you have to tell me whether the number is prime or not. So suppose I give you this 10-digit number. Now I purposefully chosen the large digit to be odd. So this is 3. So we cannot immediately tell whether this number is prime or not. So we have to write a program by which we can solve this. And actually one can check easily that this is not a prime number because this is divisible by 7. Now, the question is, can we design a program to solve this problem when we give a computer an n-digit number? So n is an arbitrary. So it can be 10, it can be 100 or 200. Now, till 2002, although this problem looks so simple, but it was not, this answer was not known. So in this 2002, these 3 scientists, actually from India, they found an algorithm whether by which you can solve this problem. That means you can find out whether a number is prime or not within a reasonable time. Now, reasonable time, mathematically speaking, it's actually called polynomial time. So that means if I want to solve an n-digit number, so the time taken is order of n to the power alpha. These are the 3 people. So it's a good news that this problem can be solved in our normal computer. Now I choose another problem, second problem. Now I will give you an integer and one has to tell the prime factors of it. So say, for example, 45. Then I know the prime factors are 5 and 2 3s. So 72, we know prime factors. Now I give you a 35-digit number. And you see that it's not easily, we can tell whether what are the prime factors. So we have to write a program. And indeed, you can write a program and you can find that the known algorithm by which you can solve in our normal classical computer, or even a most powerful computer in the world, it takes around 130 seconds if it is 35-digit. However, if I increase the number of digits, say for example 82, then the known algorithm actually takes around 1.1 year. And if I just make it double, like 200 digit, then it will take almost the age of the universe. So that means to factor an n-digit number, known algorithm in our computer takes exponentially n steps. So precisely this number of steps. So there is no efficient classical algorithm till date which can solve this problem in a reasonable time. In 1994, there was a breakthrough result which was found by Peter Shor. He showed that if we use quantum mechanics, then we can solve this problem in an efficient way. So what is efficiency? Now we can solve in the kind of logarithm scale. So if I compare now the same thing, you will see that in a classical computer, it actually takes exponential number of steps and so exponential time. Whereas in case of quantum, if we are able to build quantum computer, then it takes, or it can solve this problem in a reasonable time. So this is Peter Shor. And after this discovery, or around this time, there are several other problems which were solved by using quantum mechanics. And it was shown that using quantum mechanics, one can reduce number of steps and you can get some advantage. Now, the quantum mechanics actually, what is the basic ingredient that we are using here? Quantum physics describes microscopic particles, so atomic and subatomic level. And this was formulated around 1920s by pioneer physicists, mathematicians, scientists like Einstein, Schrödinger, Heisenberg. Even the Indian people also have a contribution like Bose and others. So there are also many important scientists whom I am missing. They are all experimentalists. So in quantum mechanics, if we now I slowly tell you that what will be the basic unit now if we want to build quantum computer, because I have already told you that if I can build a quantum computer, I can solve certain problems in a reasonable time, which a classical computer fails to do. So as I said, in classical computer, the basic unit is bit. So one of the zeros and one. On the other hand, if we build a quantum computer, then the basic unit will be qubit. So QU for quantum and bit. And what is that? This is an arbitrary two-dimensional quantum state. And the main ingredient that helps us to get this advantage is the superposition principle in quantum mechanics. It's a story of a cat, you can think. So in a classical world, we know that there can be a live cat, there can be a dead cat. But in quantum mechanics tells us that there can exist cats which can be both alive and dead at the same time. And this you can represent by like that. So you can think that these are some vectors, and these alphas and betas are some complex numbers. So pictorially speaking, if you can represent a qubit in the surface of the sphere, where the poles can be thought of as two vectors which are orthogonal, and the surface of the sphere is all the points. So there are infinite number of points, and this infinite number of points represent qubit or quantum bit. And that qubit will be the basic unit in quantum computing. Now, similarly, as we know, there are universal classical gates which can manipulate bits like AND, OR, NOT, NAND gate. Similarly, we can have quantum gates which are universal. And the examples are Hadamard gate, CNOT gate, and so on. So now the question is whether it's only a theoretical prediction. It's not. There are a lot of experimental demonstration. So it was shown that one can build 11 qubit quantum computer by using trapped ion. There was a very big news where people have shown that quantum supremacy has achieved. So this is by superconducting qubit, where Google claims that they built a quantum computer which can finish certain task in 3 minutes and 20 seconds, while a classical supercomputer requires 10,000 years, and it was in 2019. However, researchers in Beijing recently showed that this is not completely true, because if we use classical supercomputer, this job can be done in about 5 days. So really, we don't get exponential speed up. However, the quantum computer can give you some speed up, which classical computer cannot. But the speed up is not exponential. There are also several technological giants like Google, IBM, Microsoft, Intel, and there are many startup companies. They're also trying to build quantum computer. And till today, around 100 qubit, that means small scale quantum computer has already been built in the world. And so if you want to know more, you can look at these websites and you can search and can find. Here, I just want to emphasize that one thing, that making a good lantern or candle doesn't lead to LED bulb or the normal bulb. This is really a revolution in technology. Similarly, making a good classical computer doesn't lead to a quantum computer. It's really a revolution in technology, because a classical computer is based on the classical mechanical principles, classical electrodynamics, classical information theory. On the other hand, quantum computer, if you're able to build that computer, the basic principles will follow the quantum mechanical laws, which is completely different than the classical. So these will be mainly applicable for microscopic particles, as I have already said. So at HRI, we, for example, try to find a quantum system where quantum computer can be built. And we are also interested to find out quantum systems where quantum computers can be built, as well as that can be robust against any noisy environment or decoherence. Now I move to quantum communication. So if we talk about communication, that means communication involves at least two parties, say Alice and Bob. And they are situated in two distant locations, say Thiruvananthapuram and Allahabad. And Alice is a sender and Bob is a receiver. And Alice wants to send some quantum information or some information to Bob. Now, this information can be both classical or quantum. Say, for example, classical means classical computer unit. Say Alice wants to send some bits to Bob, or Alice wants to send some quantum bit or qubit to Bob. Now, in both the scenarios, one can show that if we use quantum mechanical, quantum version of that, then they can provide better efficiency than their classical counterparts. And based on that, there was some protocol were designed, and these are quantum dense coding and quantum teleportation. So just briefly, I want to tell you about quantum teleportation. Suppose Alice wants to send an arbitrary qubit that I have already talked about to Bob. Now, classically, if we use classical device, the devices that we are using now, you require infinite amount of classical communication. That means infinite number of bits. On the other hand, if Alice and Bob a priori share a quantum state, then one can show that the quantum communication device requires only 2 bits of classical communication. So you can get infinite resource reductions by using quantum communication device. This is quantum teleportation, discovered in 1993 by the 6 people. So the main resource that are used to build quantum communication device is this shared state between Alice and Bob. And this is the main ingredient, and this is known as entanglement. So very briefly, what is entanglement? This is again a shared state between Alice and Bob, which can be written like that, where X and capital X and small x and capital Y, small y are all complex number. These are the unentangled or useless states. And these states can be prepared by Alice and Bob, even when they are situated in far apart location. On the other hand, to create entangled state, Alice and Bob's particles should interact. That means if they are situated in far apart location, Alice and Bob will not be able to prepare these states. So to prepare these states, there should be some source where Alice will prepare. Say, I want to send some information from Allahabad to Thiruvananthapuram. So then I choose some node, say, for example, which can be situated in Delhi, for example. That Delhi node can prepare the entangled state, send one particle to Thiruvananthapuram, another particle to Allahabad, and then we can perform the quantum teleportation or the communication. So there should be some service provider you can think of. So this is the quantum bridge that we want to build between sender and receivers, which gives us a power to solve or to send certain things, or to send certain or to perform certain tasks, which is not possible by using classical device. Here, I just want to emphasize that although I have defined very briefly what is entangled states, but the definition is clear, but still it is not known that given a quantum set, whether we will always be able to find out whether the state is entangled or not. So you can think that the entangled states as fishes. Okay, so you want to actually detect those fishes, or you want to capture these fishes. That means you have to create some nets. Now, if the state is very less entangled, then you require a finer net, and that's more difficult part. And we still don't know how to really catch those fishes. So now in the world, people are trying to build quantum communication network. This is one of the research area that are nowadays people are exploring. So to instead of sharing entangled state, or instead of communicate, we are thinking about not the communication between only a single sender and single receiver, but quantum network should involve many senders and many receivers. And there we want to do information transmission. And for example, at HRI, we are trying to we have proposed certain tasks, certain communication network, how to build them, but these are very initial work, because there are a lot of directions which we still don't understand, and people are trying to work all over the world. So there are also a lot of experimental achievements in this area. So people usually use photons to share entangled states, and till now the maximum distance in which entangled states can be created by using photons is 1200 kilometers. This is a breakthrough experiment done in China, led by Professor Pan. So that means we can now perform, say, the teleportation experiment between two cities like Kolkata, Guwahati, Mumbai, Chennai, because they are around 1300 kilometers away. Similarly, people are also trying to build how to really do a experiment in when we want to build communication network which involves multiple senders and receivers. I have some time, 3-4 minutes. Hello?
Yes, please go ahead.
Oh, okay, thank you. Okay, so the last part I will talk about quantum communication with security. So up to now, I have only discussed the scenario where there is a sender and receiver, and sender wants to send some information to the receiver. Now I put another layer of complication. So I put in eavesdropper in between sender and the receiver. So, so suppose sender wants to send some information to the receiver, and eavesdropper's aim is to gather as much information as possible that sender is sending to the receiver. On the other hand, sender, that means Alice's aim is to encode information in such a way that eavesdropper cannot gather any information. So we are actually probably every day now, we use this scenario, because when we do internet banking, right? So we want to communicate our information, or the login or password or any information, any transactions only with the bank. We don't want that any third party can gather information about that. So this is true for any internet transaction. This is also an important issue in national security. So, and this is true, the secure communication is important from ancient time, okay? And probably many of you have heard the massacre that was happened during World War II, when there was some miscommunications between the same people. So in classical cryptographic system, the security is based on the belief that some of the mathematical problems cannot be solved in a classical computer in a reasonable time. And as you can now guess that one of the problems that I have already talked about, prime factors of a given integer. Now, the twist in this whole issue is the following, that I have already said that these problems can now be solved if we build a quantum computer. And that means that if we build a quantum computer, then all the crypto systems that we are using now will be insecure. So what is the way out? Now, the remedy also comes from the quantum mechanics, because if we now build a quantum cryptographic system based on the quantum mechanical principle, that means the security of cryptography is now based on the validity of quantum mechanics, then that remains secure even when we have a quantum computer. And this was developed by 3 people. So this is Bennett, Bennett, Brassard, and Arthur Eckert. They proposed in 1984 and 1991. In quantum secure communications, we want to generate quantum key between sender and receiver by randomly generated quantum states. And the important also point is that here in quantum world or in quantum cryptography, presence of eavesdropper can be detected just because we something called quantum no cloning theorem. Now, this is also not only theory, it was actually successfully demonstrated long back in 2001 between two points in under Lake Geneva. And now actually it's kind of reality because they have used that in Football World Cup in South Africa, in Geneva elections where they use quantum crypto system. And also at HRI, we work on that. I'm not going into this detail because, so we also here interested to build the quantum crypto system, which involves multiple senders and multiple receivers. So this is one of the now primary directions which people are trying to explore. And there the security will be much more complicated because there are multiple senders and multiple receivers are connected by different channels, multiple channels, and then each channels can have some eavesdropper. Either they can attack jointly or they can attack individually, and that makes the scenarios more complicated mathematically, and also there are other issues. And so here I just end with some note that there are some India's effort on building quantum technology. Department of Science and Technology has launched a program called Quest, Quantum Enabled Science and Technology, which has kind of four directions where the people are doing research. So quantum communications with quantum optics, which I have talked, quantum technology with superconducting qubits. So they want to build quantum computer or other quantum technologies by using superconducting qubit, also ultra-cold atom and Enable and NV Center. And possibly all of you have heard the recent development where there is some national quantum mission where cabinet approves some 6,000 crores where scientists will be interested to build quantum computer, as well as there are other quantum devices like quantum sensors and other things. So, so I think I am able to tell you at least to give you the flavor that quantum mechanics can revolutionize computation and communication capabilities with and without security, and this leads to a new era. So already, as I said, quantum cryptography is the reality, but quantum internet, like quantum network or communication network, is still in a very initial stage. And at the same time, quantum computer, we have a small scale quantum computer like 100 qubits and so on, but probably our aim is to build quantum computer consisting or containing at least 1,000 to 3,000 qubits, where really we can show quantum advantage, which is far from the reality. But there are some projections like 2035, probably some of them will be in reality. So I must acknowledge my team. So these are the people who are working with me, mostly PhD students, and Olga is a postdoc, some master students, and also some faculties who are constantly working with me. So some of the results I have already shown. And this is my group at HRI, where these two are actually the alumni. And this is the entire QIC group at HRI. So if you're interested, you can write to me and write to any of faculty members. So this QIC group is led by Professor Ujjwal Sen, and the new faculty now, Professor Debbraj Rakshit, and all our PhDs and postdocs. So thank you very much for your attention.
Yeah, thank you very much, Professor Aditi. So are there any questions? Anybody wants to ask any questions, please? Any questions, please? Yeah, 1 minute. There is a question.
This year's Nobel Prize is connected with this quantum entanglement.
Yeah.
Same. it was quite confusing, but here we didn't find that. Can you just put some light on that? What was the Nobel Prize connected with this?
Yeah. Yeah, so the entangled state that I have very briefly discussed. In experiments, so the three people who got the Nobel Prize, Thaler Aspect, Anton Zeilinger, and Clauser, so they are able to demonstrate entangled states in experiments by using photons, which I have mentioned that this Chinese group has done created an entangled state between 1,000 kilometers. But initially they are created in the laboratory, and these three people have created entangled state by using photons, polarization degrees of freedom, this entangled state. And but creating entangled state is not enough, because one has to, as I have already mentioned, that it's difficult to detect or to confirm whether the state that has been created between two parties are really entangled or not. So one has to prove it. And in case of Clauser, Zeilinger, and an aspect, they have contributed in that directions because they use something called Bell inequality, and by confirming that whether the state is entangled or not. So they that kind of still people use Bell inequality as a detector to detect entangled state in laboratories. Now, I must mention that Bell inequality is not only used for detecting entangled state, but it also has some fundamental it also answers some fundamental questions in quantum mechanics raised by Einstein, Podolsky, and Rosen in 1935, whether the quantum mechanics is complete or not. So this has both. So the recognition of their experimental results from both sides. So they are kind of starting off all the quantum technologies that people are now trying to build, because the entangled state is the basic ingredient to build all the quantum technologies. I mean, most of the quantum technologies. And at the same time, it also answers some fundamental questions in quantum mechanics.
Okay, thank you. Any other questions, please? So I have a question. So this quantum entanglement is a desirable thing, because you were asking about transportation of the entangled. So is it something that we want to have, or we want to detect?
Yeah. So entangled states are kind of as I said, that this is the resource to obtain any benefit if we want to get any benefit, for example, in quantum communication technologies. So that is requirement. So if we cannot really, if Alice and Bob, which I was always talking about, so if Alice and Bob doesn't share this entangled states, one cannot perform, say, quantum teleportation experiment or any other quantum communication, quantum communication technologies we cannot build. But in case of quantum computation, it is still not clear whether really we need entangled states or not to obtain this speed up. At the same time, there are other technologies where also things are not very clear, but in many scenarios, more or less, people are convinced that to build quantum technologies, entangled states are one of the important resources.
Okay, thank you very much. If there are no other questions, okay, let us thank the speaker once again.
So there are some questions in the chat. Should I?
Sorry, there are some questions. Sorry, on the. Can you see?
Yeah. Yeah, I can. Can there be any hybrid models of generative AI and quantum computing? Yes, it is actually. That's a nice question, because as I already said, that the photons are good physical systems to actually build communication technologies. On the other hand, photons are not very good for computation because they interact less, so it's hard to implement. many quantum gates which we require to manipulate quantum states. And so people are now trying to build something which are kind of a hybrid model. So where they are thinking to build, say, small scale computer by using superconducting or trapped ions. And then there are several such clusters they want to build by, say, trapped ion, and where they want to communicate between these two clusters by using photons. So this is one, I mean, this is just one proposal that people are trying. So there are a lot of work now going on this hybrid model. So mathematically speaking, so you have to work on a one system. So in this entire entangled states, or these things are, we are talking about a tensor product Hilbert space. So you can think that when we talk about a hybrid system, then one of the dimension of the Hilbert space will be finite, another can be infinite. And so the algebra will be much more complicated, but it turns out to be useful for many information processing tasks.
Yeah, thank you.
Are there any other questions online? Okay, so since there are no other questions online and offline, so we end the session now by thanking Professor Aditi Day for giving us a very good idea of quantum computing and its importance. And so thank you very much, Professor.